Muchísimas gracias, profesora Díaz.
Thank you very much, Professor Díaz. And our last speaker won a Nobel Prize for Physics in 1995 for discovering the first exoplanet, or in other words, the first planet to be discovered outside our solar system. Since that time, his research team has helped find another 250 exoplanets, developing experimental techniques and astronomic tools for that very purpose. So today we have the pleasure of welcoming Didier Queloz, the founding director of the Leverhulme Centre for Life at the University of Cambridge, and also of the ETHZ Centre for the Origin and Prevalence of Life in Zurich. The title of his lecture is The Exoplanet Revolution. Professor Queloz, the floor is yours.
Thank you very much. It's a pleasure to be here. What a wonderful place. So, well, we are on the planet Earth, orbiting a star, the Sun. We are surrounded by 100 billion stars in the galaxy, about. There are millions and millions of galaxies in the universe. Well, this is something I'm pretty sure you're all aware of. It took us, the science, 100 years to build up that picture recently, well, starting from Newton, even further down. Well, the last chapter of that story happened in the last 30 years, which is whether there are planets orbiting other stars amongst the galaxies, and the billions of stars of the galaxies, and the millions of galaxies in the universe. And this last episode is quite often compared to a revolution. And I will try to go with you through this revolution, try to explain what is a revolution actually. And I will even push it further. It's a beginning, something even bigger, which is related to understanding life in the general sense in the universe. How do you find a planet? Why it took so long to detect planets on other stars? Well, the problem you have essentially is the star. So if you point one telescope, even the biggest telescope you can find, you will be essentially blind by so much light that shines from the star. And you won't see the planet just next to it because it's too dark. It's like looking at a car, the light from a car just beaming at you. Now, to detect planet, you have to use tricks. And the tricks is essentially looking at the star and trying to find whether there is something on the star I can use to find the planet. So what we do is we're using the gravity as a trick. Because when you have a planet orbiting the star, as you see it in the back, it makes the star moving around the center of gravity of the system. And you can use this to compute the speed of the star using an effect which is called the Doppler effect that will change the light, the color of the light of the wavelength, if you're familiar with this terminology, to find out that there is a star. And if you're lucky, at the moment your star is just crossing the line of sight between you, the telescope, and the star, you create a tiny shadow on the star, which corresponds to the observer to like a tiny cloud passing on the sun during a sun day, slight decrease of the amount of light coming from the sun. And from this, you can find the size of the planet. This is by these two techniques, essentially, that we know most of the planet orbiting other star. And from that, we know the mass of the planet, we know the size of the planet, and we know the distance between the planet and the star, or the orbits, or the time the planet takes to go around. So I could go along 30 years of discovery. I decided to give you the overview about all the planets we know. And this two-picture diagram give you the overview. So think about this. This is a diagram when you have the period of the orbit, which corresponds to how far the planet is orbiting the star, and then the size, called the radius, and then the mass of the planet. On this diagram, I'm sure you recognize Jupiter on the top right, and you recognize Earth and Venus. Every point, every dot you have on this diagram corresponds to a planet that has been detected so far. There is about 5,000 on these diagrams, and it keeps changing every day. So what is fascinating here is the global picture that we have right now on the system. And in a way, it was a shocking picture, because the planets are not exactly the way we thought they should be, and it's obvious on this diagram. Well, you clearly see that the planets, they are sitting here at a location that doesn't match Jupiter, some maybe a little bit, but not all, and the Earth and Venus are completely alone in this diagram. So to help you to understand that, I have to add something else here, which is what's called the limit of the technology that we're using today to detect planets. So this is these two lines here. So now anything you have on the right side, we can detect. Anything on the left side for you, and then on the right side, you can't detect. So if I focus on the part that we can detect, well, you realize that all this planet that we have here, essentially we have not any of that kind in the solar system. We're talking about planets in the case of this one or that one that are the same groups, that are of the size of the mass of Jupiter, but with an orbit of a few days, meaning they are literally roasted by the fact they're so close to the sun. So too much light, it's very hot. We call that the hot Jupiter. We have all this group, which is a massive amount of planets, that corresponds to a group which is quite often called the super-Earth, mini-Neptunes, because they are sitting into a regime that corresponds to the size and the mass from Earth and above. But again, the period and the distance to the star is very short. So we're talking about planets that have orbit of a few days, even some of them less than a day. It's shorter than the orbit of Mercury. So essentially, all the planets we have detected, almost the vast majority of them, they would be sitting within the orbit of Mercury in the solar system. And I can tell you, in the orbit of Mercury, there is nothing in the solar system. So all these planets are completely different from the solar system. We have some of them that looks a bit similar. This is the one sitting over there here that a bit in the same category than Jupiter. So it's not completely extravagant, but most of them are really different. Now, to really make this a rational argument, this diagram is very misleading because there's a lot of systematics in the way we're searching for planets right now. So I have to bring you what's called the occurrence, which is the likelihood that there is a planet on a star. So you have to imagine when you look at a star at night, the number you will see will tell you the probability that you will find a planet of that category into each of these stars. And the number are striking. There is very few of them that belongs to the category what's called the hot Jupiter, a few percent. So this is why when we started 30 years ago to search for planet with a machine that was called LOD, we had a group of stars, about 140 to look for, and actually we found 2 into these groups. So this is the reason why we had very few in our sample there. Well, the big surprise is we realized that this group of planets that are called super-Earth or mini-Neptunes, they are the vast majority of the system you have in the galaxy, actually. You have more than 50%, up to 80% chance AT to have a planet of that kind orbiting a star. So in a way, it solved one problem, which is what is the likelihood to find a planet on a star? Well, essentially, it's almost 100%. So planets are being formed very naturally in the process when you form the star. But the planet you end up with are not exactly the one we have in the solar system. Actually, there is maybe only a few numbers of the stars that have a planet like the own solar system. And that was the revolutions. We changed the perspective. We are not the unique example of the way a planet exists on other stars. We know there are plenty of them, but we know there are plenty of them that are different. Well, the amount of data we're getting can be combined, and actually you can combine at the same time the measurement of the mass, measurement of the size of some of these planets to produce an information that we call the density that gives you some element about the nature. What are these planets made of? How far they are similar to the one in the solar system? And that this is this kind of a diagram when you have the mass of the planet and the size of the planet on the other side. And all the kind of dots you see with the arrow bar here on this diagram are actual measurements of planets orbiting other stars. And to help you to read them, I added a little bit to help you to read known planet. Well, we have Jupiter and Saturn. This is where they're sitting. Actually, they are along a line, which you see with hatches here, that define the typical structure of a planet, which is called a giant planet. So any planet that would have the same composition that Jupiter or Saturn, which essentially is the same amount of material you have in the sun, it's just far less. You need 1,000 Jupiter to make the sun in terms of amount of material, but they are hydrogen and helium essentially there. They will be sitting along that line. When you come to Neptune, which is over there, you see Neptune doesn't really, cannot be explained with the same model of Jupiter and Saturn. Actually, Neptune, for the same mass, because this is the mass here, is much more compact, is much denser. Well, the reason is because Neptune has very few hydrogen. So hydrogen makes the planet bigger. And this is quite often the reason why we consider Neptune as a failed giant planet. Neptune never had the time in the formation process to get all the gas in a similar way than Jupiter or Saturn. And this is where Neptune is sitting. Now, we have plenty of other planets that are denser than Neptune and with size going even down to 1. This is 1 Earth size, 1 Earth mass, and this is 1 Earth size here. So we have a kind of a cloud of object. And it's really difficult to get a sense what they are. The only thing we can do here is to help you to read this diagram and add maybe the Earth, where the Earth would be in terms of density. It's what we call a rocky planet. And this is this green line here. So anything along this green line would have a density similar than the Earth. And it's likely to be a planet, kind of rocky planet, in the same league than the Earth or Venus. And you see the Earth would be sitting here, 1 Earth mass and 1 radius of the Earth. Now, in between, just to confuse you even further, I added an impossible planet, which is what called a planet of water, water world. You take water and you make a planet. It's unlikely it exists, at least certainly not completely by water. But to show you that there is, by playing with the structure of the planet, you can reproduce part of this diagram. And what we have here is a huge diversity of structure. Some of them are in between. Some of them looks more like Neptune, or maybe mini-Neptune, or super-Earth, or water world, and you can invent a lot of terminology here. That is simply a way to express that we just don't know what we're doing. But there is something we know, is the dividing line between the planet like the solar system, what we call the telluric planet, or the rocky planet, Mercury, Venus, Earth, and Mars, and the giant planet, this big jump between these two categories, is just something specific to our own system. It's not something that you see as a generic situations for all the planets in the universe, because there is plenty of diversity. So we had to talk about the diversity on life on Earth, and this is the diversity of the planet in our galaxies. And that came as a complete surprise, and frankly, right now we have a kind of a good overall picture how you can do that, but we don't understand the specifics. So it's still a subject of understanding and modeling how come do we have such a diversity. Now, we don't only detect planet and measure the mass and the size of the planet, we can do much more than that. And I would like to share with you the kind of data we can now collect on this other world, very far away. The trick is this transit moment. So there is these special configurations where it happened that you are looking at the system with the orbit of the planet crossing the disk of the star. That produced two very special moments. One of them, when the star is hiding the planet, when the planet is behind, it's called an eclipse. That is an interesting moment because, I mean, you may ask yourself why. I mean, we don't care, the planet is behind. But actually for us, it's really interesting because the star is only detected at that moment. So we know if you use any equipment to look at the star, there is nothing that comes from the planet because the planet is just behind. As soon as the planet pops up and gets visible, what we do see with the equipment is a little bit of an increase of the light that we receive from the system, and a slight difference between the time when the planet was behind and the planet appears give us a direct indications of the amount of energy coming from the planet itself. From that, we can compute the temperature, the mean temperature of the planet, but we can also study the nature of the reflecting atmosphere, like the moon. The moon, you get the reflections from the light of the moon. So this is one of the elements of the special configuration we're using. The other one is when the planet goes in front. Because at that moment, actually, the planet is hiding the star. So it removes part of the light from the star, and the amount of light that's being removed is proportional to the area that the planet is blocking. So if the planet would have the size of the whole star, it would completely remove the whole light. Actually, it only removes a fraction because the planet is typically, in the case of Jupiter, is 10 times smaller than our sun. So the area you remove is 1%. So a few percent you remove at that moment. But actually, you can do way more than that if you carefully study the light that comes at that moment. And to better understand that, I will share with you a couple of pictures that is taken from the space stations. So this is a picture in the visible. You can do that with your cell phone. And when you see something which is, to me, magical, I was mentioned before, is the biological, tiny biological part of the atmosphere. The reason why we are alive, the biosphere is very tiny, it's 10 kilometers on something which is 6,000 kilometers diameter. This is what you do see, and actually this is the blue sky, which corresponds to what we call the Rayleigh scattering of the light by the atmosphere. Now, if I observe at the very same moment that special configuration, I picked that on purpose because it's to help you to get a sense of the size of the atmosphere, but I observe in the infrared. Infrared is a thermal you sense with your skin. Your skin is a thermal detector for the infrared, and you feel the heat. So if I do that in the infrared, I have a different picture, and this is the one in the infrared. So if you pay attention to the distance between the moon and the Earth, you may have noticed the distance has increased, right? If I go back, you see? Because this is a picture of the Earth without the atmosphere. Why? Because the thermal emission at that wavelength come from the surface of the planet. That's the heat of the planet, temperature of the planet that we see here. So now you get already something interesting here. The size of the planet depends on the color I observe the planet, or the wavelength, right? So I couldn't go in the opposite way, very extreme. I use a very specific wavelength, which is sensitive to one gas that is protecting us from the deadly UV radiations right now from the sun, which is the ozone. So if I do that, I observe with a light that is sensitive to the ozone in the sense that the ozone will absorb the light, will take that light and prevent the light to cross. If I do that, I reach a much bigger atmosphere. It's pretty clear here. You see this, no, it's a bigger atmosphere you have there, 50 kilometers. Okay, so I think you got my message. The size of the planet depends on the wavelength you observe it. Because you observe a transit, if you observe the transit in different wavelengths, you will see different size. And that's called transit spectroscopy. We started doing that about 10 years ago, but now we have pushed the boundary to a level which is amazing. And I want to show you the very last result from the transit spectroscopy measurements, which is this diagram that was published 2 weeks ago. One exoplanet, which is a Neptune size, it's a Neptune size exoplanet, that we observe at different color. You have the different color, you have the blue part here, kind of, it's 1 micron, and this is the red part here. And what you see is the amount of light blocked, it's all the point that goes up and down, up and down, up and down. So the amount of light blocked, or the size of the planet, is changing depending of the color I'm looking, the transit. It's a very complicated diagram, and actually to understand this diagram, you need to do inverse modeling. You need to inverse the model and trying to find out how can I explain this amazing structure with up and down going on this data. And you find out that you can explain that, and there's not many solutions, with an atmosphere, a specific atmosphere. And you can say, look, in this atmosphere there is special molecules, and these are the molecules, methanes, carbon dioxide. And this is a very interesting dimethyl sulfide. This is a very interesting biological molecule here you have. So this is the first time that such a complex atmosphere that with especially methanes and carbon dioxide has been detected in astronomy. It's just the beginning, because this is just the very first. I know there is a dozen of these studies coming up, and possibly the similar kind of measurement on smaller stars. Right, so we're detecting atmosphere of planet. Well, so it means we can find out what is in the atmosphere of the planet. So what does it really mean practically from an astrophysicist? So of course you can look at the atmosphere of the Earth today and can say, okay, fine, we can look at the kind of stuff today, but you have to be a little bit careful here, because the Earth is a kind of a living planet, is not exactly the way you started with compared to other planets. So I have to just move up to another chapter here, which is Earth history, and then to connect it with exoplanets. This is the story of the Earth. If you study Earth science, that you would learn. It's like a bit of a clock. You start here and you turn around, and then this is what is today. So this diagram is meant to explain to you that the Earth has evolved a lot from the beginning. So when you form the Earth as an astronomical object, you have a very different element into the Earth. And a lot of the light gas, like hydrogen and helium, are gone, they lose. There's a lot of stuff that comes feeding the surface of the Earth, and all this meteoritic impact, full of carbon that comes from the icy zone of the solar system, full of CO2 in the outer part. So a ton of carbonate is falling on the Earth at that moment. Possibly some water as well that you're coming by the way, because there's also a lot of water in comets. And you really feed the planet with things that was not there when you formed the planet. And then the planet gets structure, the heavy components are sinking down, iron, you start the iron core, the magnetic field is starting at some point, and you end up with an atmosphere which is dominated by volcano with a lot of CO2, SO2. This is what we call a kind of neutral atmosphere for a planet. You have this extreme example of an atmosphere like that on Venus. Now, on Earth, at some point, something happened that we call the prebiotic moment. Pre means before, bio is related to life. So there is something is going on. There is a chemistry going on here. And then everything changed. And it was clearly explained at the last talk then the main effect is life develops, starts, is generated, and then not only is there, it just grow and strive and populate all the kind of niches you can think about it. And now it mixed with the planet, because the planet is part of the life is part of the planet, and the life is terraforming everything. The oxygen we're breathing, the carbon that rhino made of, it all comes from the life. And that moment is the situation we are all on Earth. So this is the story of the Earth. Now, what is fascinating as an astrophysicist is if I look at that planet at different moment, what I do see with my telescope, using the technology I mentioned to you before, well, what I do see is a spectra, similarly to what I did with molecules, exactly the same kind of molecules. But what is pretty fascinating is the molecules at the time before you have life, which is the Archean moment, the beginning of life, and then when today, it's a completely different picture. So you have a completely another atmosphere on the planet. And what is great for me, it's not a detail, it's a massive effect. We are completely changing. You don't need to be a physicist to see there's a difference into that diagram on that one. It's obvious. And that is something we can do, if you believe the data I showed you before. So we can look for that now on other planets. Well, I think it opens a lot of interesting questions right now. So you all know this famous picture, I hope you know. This is the famous blue dot picture. That was 50 years ago. This was a picture that was amazing at that time as a mental element to look what we were tiny in the middle of nowhere. But that has been taken by a spacecraft in the solar system, looking back at the Earth. Well, what you would do if you would analyze the data at that moment, you will find this, which is the kind of a low-resolution spectra response, which is all the components that I mentioned in more detail before, the water, the CO2, the oxygens, the nitrogen, and so on, all what we have now in the atmosphere. And again, it's massive. It's not a tiny detail. No, what I do claim is tomorrow we will be able to do that. We will not only going to do transit and radial velocity and transit spectroscopy with the James Webb telescope that I showed you before, but we'll do that because we're building amazing equipment. This is one of the very big telescopes under construction right now. It's an extremely large telescope being built in Chile. It was on the best site, best sky on the planet right now, and this will become operational in a couple of years, and part of the program is to do exactly that. What exactly that is that? Well, actually, this is looking for life in the universe. So does it make sense? Is it something we can do? And I would like to share some thoughts about that for you to make your own mind, whether it's a crazy idea or whether it makes sense now to do that. At least you understood that we can measure spectra on planets quite far away and I can detect something. But what does it mean on life? Well, let's first start with maybe a statement. Usually at that moment, all the people that are studying biology, they say, this guy is crazy because, I mean, life is too complicated. There's no way it can happen elsewhere. It's unique, it's special. And for me, I feel really at ease because I will use as a backup another Nobel laureate, which is Christian de Duve, biochemist. We had this fantastic statement. I would like to use this statement to help you to understand what's going on. Christian has a very simple statement. He said, life is an obligatory manifestation of matter. It's imprinted into the matter. It's part of the general pattern of this universe. So if it happens here, it must happen elsewhere. There's nothing special. If you create a star that is called a sun, here there must be other stars also elsewhere. In terms of astrophysics, it opened the field in a kind of a different way. If you think about that and translate that for an astrophysicist, well, I would just start from the beginning. I say, okay, you start the universe with the Big Bang. It's a fascinating moment, but how boring, because you create time, space, maybe matter, well, hydrogen. That's it. Not much. Well, actually, the law of physics are acting already. Gravity, bringing stuff together, and you making stars, right? The stars are fascinating machinery because they start a new field that's called chemistry. Because stars are making the chemistry possible. All the elements you have in the Mendeleev table, they are being produced in a star. All your atoms here are being produced by the star, not by the Big Bang. The Big Bang enabled it, but the stars are making it. But the stars are making way more. They're making the lab for the biochemist. Well, biochemistry is going on in the universe, but it's very cold, it's very slow, you have the UV radiations. You can do some kind of alcoholic chain, stuff like that, yes. It's very limited. The real place to make the real chemistry is on planets, whatever planet you have in mind. So it happens that at the time you form the star, it's part of the fabric of the universe, the system enabled to make planets of all kinds. And on this planet, you start doing chemistry with a different temperature, with different conditions. Maybe you had rain, maybe you had drying out, maybe you had lake, maybe you don't have lake, maybe you have big oceans. Doesn't matter. Chemistry, biochemistry is going on. And that biochemistry is not possible without that. So you see already, Christian de Duvalier, who would have guessed when you look at the Big Bang, you will start making biochemistry on the planet a bit later. Well, it's in the fabric of the universe. And comes life. At some point, matter transition into life. So right now, we tend to divide the two. We tend to see the matter on one side and life on the other side. Well, actually, at some point, it transitioned, right? And this is what about. So to me, as a physicist, it's just the last moment. There's nothing more different. Starting from the Big Bang, you create all these elements, you do the chemistry, and then you start life. So to me, the start of life is a non-issue. It has to happen many times, everywhere. The question is not starting life, is how far you start, and you keep going, you strive, you populate. Maybe in that sense, the Earth is special, because you can look at other sites on the solar system. Mars, Venus, well, maybe Mars, in the past, started life. Lost now the atmosphere, lost the water. Maybe there are some now, but there may be some left over. Venus, maybe was the same 3 billion years ago, 4 billion years than the Sun, than the Earth, with water, oceans, blue planet. Maybe we had 2 blue planets at that moment in the system. Because of the fact that Venus doesn't, recycle the CO2 by lack of plate tectonic, well, maybe by lack of water, because the plate tectonic needs water to work, then everything stopped, and then the CO2 started rising up, and you had this thermal final greenhouse effect. So you see it's interesting, the element of starting life and developing life. Now, what does it mean finding life? Practically, the element. So I have to make a jump here, and I have to share with you life seen with the eyes of a biologist and why it's challenging as a problem. This is the descriptions, what is going on at the microsecond level in your body right now. It's the same things going on in the plant outside. It's the same things going on everywhere. That's a magical process that maintain life alive on this planet. So Wool diagram, Wool element, actually is based on 3 elements. They're playing together, a mechanism that replicate. We use RNA in that case. It's a unique mechanism that's shared by any living organism on Earth right now. It's the way you produce the energy. You need to produce the energy. You cannot cook and bring UV. You have to make the energy from chemistry process, and you have to make sure you don't dilute into the oceans or whatever. So you have to bring some compartment mechanism, and this compartment should be secure enough, but also enable you to get in and out. Otherwise, you cannot get feed stock and not remove things you need to remove. So it's very complicated. This is what is going on right now. So I agree, this is fascinating, but this is a process here that happened in a 4 billion gigaton years. 4 billion years, really, on evolutions, what we're having right now. And that is the big challenges, because right now we're seeing, in a sense, the end product of a long process that started a long time ago. And this process is this. It's the tree of life seen with the time in addition. So the time tick in the middle, and then goes, and goes here with the time, and you see all this huge diversity of alive organism we have on Earth. The human is here. We come very late in the process here. But we do see all of this right now. This is today life on Earth. Well, actually, the challenge here is, well, it's fantastic diversity to study. It's fascinating. But what is fascinating is everything started somewhere here from the early stage. And how do you connect something you have as of today with the element that enable life to start? And that's a tremendous, difficult problem, I think, to face. And I do think by observing plenty of different planets, including going to Mars and Venus, this is helping us to build a more comprehensive picture to solve this tremendous problem. What happened there? No, there is only one thing we can say for sure, at least up to now, that is helping us. Well, life is not created today. We don't create life. And it was already said in another way by my previous speaker. We just replicate. We are replication. I'm sorry to tell you, you're all replication. Your brain tells you, your consciousness tells you, you're unique. But it's just a trick of your brain. You're just a replicate. Nothing else, nothing more. Fantastic replicate, but still a replicate. So why so? Because the condition to create life from scratch are not met. At least nobody has detected any such of life creation on Earth in any place that we looked at as of today. And there is a good reason for that, because at the time life started on Earth, it was almost 4 billion years ago, about 500 million years after you created the Earth. And at that moment, San Sebastian here was looking like that. It's a different planet. I told you already that. But that's the beginning of life. This is the good place to make life. Sounds a bit funny, but that's what it is, because at that moment, the atmosphere was completely different. It was a neutral, SO2, there's water was there, a lot of CO2 in the atmosphere, a lot of impact from comet, way more than now. There were way more of cometary impact. Volcanic activity, very likely extremely high as well. Maybe a lot of oceans, we're not sure exactly, but the guess is very tiny continent. But this is the chemistry of life. This is the lab where life started. Now, I think we all understand the challenge right now we're facing, because you can observe many different planets, getting an idea what they look like. You know that at some point, that was the condition for life, so you need to connect the dots. And connecting the dots is connecting two things which is not usually been connected. It's the biochemistry of life. Could you start to produce the biochemistry of life in a lab? Could you try to track or deconstruct life as we know it today? Not specifically in terms of process that enable, without all the tricks that life is using right now, by just replicating, but creating. But at the same time, having the right conditions, the ecological conditions that enable this to happen, the right ingredients, the right processes, and not only happening, but also develop. Then you start life, but then you strive, and you're competitive, and you grow, and you start complexify, and so on and so on. Remember, it took a long time until life became more complex. And there's a very long process until the conditions was met, essentially by the great oxygenations mentioned later for life to strive at the level. So this is a bit of what we're trying to do. And this is the revolutionary aspect of the planet. It happens that detecting all these many planets is opening a new window of opportunity. Combined with the Mars sample return, there is a hope that we will see maybe early trace of the early chemistry that enabled the beginning of life. Don't think we're going to get fossil, but certainly possibly some hint about the condition on Mars that would be interesting to compare. And that never happened. We never brought back a sample from another planet really on Earth. And this is going to happen. That's just the beginning. There will be way more in the future. In terms of what we are trying to doing is this kind of very complex diagram that reflects the complexity, is the chemistry, this is of life, the astronomy perspective, which is going to the diversity, limited information, because we cannot go there and grab a piece, but we are seeing so many stars in so many configurations and through the different time evolution of the star, and at the same time combining with a deep understanding of the planetology of the planet where we can go. And I'm not limiting here myself to Mars and Venus, because these two planets we will go. Even Venus will be challenging, but that's a material science problem right now, to build a spacecraft that would survive to the condition of Venus. But I can also think about some satellite into giant planet. There's Titan, there is Enceladus, there's a lot of these different satellites when the conditions are very different from the rocky planet, but we know there is a huge diversity of biochemistry going on, and we are really, really, really looking forward to going there. So this is what is going on. This is why I started the centers that was mentioned, is trying to help at the beginning of a long story which is looking at life as a general pattern of the physics conditions built into the universe in a global way. Thank you very much.